Bruce Director titled his class AI, Boone or Boondoggle. And he proposes to uh, discuss AI from the standpoint of Lyndon LaRouche's Science of Physical Economy, its current state, truth versus hype, uh, the how does AI work? Can machines think? What can it do for the real economy? Bruce worked closely with Lyndon LaRouche for decades, precisely on this issue and other related scientific issues. So, with that, let me pass it to Bruce.
Thanks, Tony. Good to be here this evening. And actually, I was asked by several people if I could present something on the subject because it's such a hot topic right now. And not just as a subject, but also as a financial matter, since so much of the stock market is being kept up by AI investments, and a huge amount of the economy is being focused on AI. And you hear President Trump talk about how the U.S. has to be the AI leader in the world. And there's a lot of hype and also a lot of mythology about AI. So I thought it would be useful to discuss this from the standpoint of LaRouche's ideas, because LaRouche actually dealt with this question from the very beginning of his career as an economist, and was very central to his whole views on politics. So we'll get into more of the hype and, where it stands with the economy. But let me begin with just the whole idea of what is AI. It's not really new. I mean, it's new now and gotten a lot of attention because of the speed and complexity of microprocessors, which allow for the processing of electronically of at very high speeds and very complex processes, and with parallel processing, billions and billions and billions of computations can be done very, very quickly. So the degree, the volume of processing is dramatically increased, and it enabled the construction of some very sophisticated processes, such as large language models, so forth. But the principles of AI are not new, and so I want to start there. Let me just also say at the beginning, I'm not an AI doomer that says that AI is going to take over the world and destroy us, nor am I someone who says that AI has absolutely no uses, no productive uses, and isn't going to make much of an effect on our economy. And we could talk about that in more detail, but I think everybody's coming to the realization that there's been a huge amount of investment in AI processes. A whole bunch of different AI systems are available to people, both for free and on a subscription basis. And and are being used by companies. But whether or not they're actually increasing productivity is a whole nother question, and we'll get into that in more detail. So I leave the question open as to what actual effect on productivity AI, what people are calling AI, will have. And I'll give you some examples as we go along. But I think it's important to just demystify it, because there's a lot, as I say, there's a lot of hype. There's a lot of stories about it, both for and against. And I think they all sort of miss the point. And if you step back and think about what we're actually dealing with here, it helps make the whole discussion more clear. So, as I say, AI is not new as an idea, but in fact, it was even sort of mooted centuries ago with the advent of the first calculating machines by Leibniz, Charles Babbage, and others. But it became a big topic of discussion in the 1940s, basically, with the advent of electronic data processing, both first with vacuum tube and other types of switches, and later transistors, and then microprocessors, and so on and so forth. And in the 1940s, LaRouche took this on because some of the early proponents of AI, like Norbert Wiener and John von Neumann and others, believed that with these more advanced and technically advanced machines, that human thought and human thinking can be reduced, or can be ultimately imitated by a machine. And this at this time was relatively theoretical. And LaRouche, though, took it on because he believed at the time that it was the proposal itself was problematic, not because of what it said about machines, but because of what the proponents of it were saying about the human mind. Now, he had two points of attack. One was a formal logical, I guess you could characterize it, criticism of the arguments of Wiener, von Neumann, Shannon, and others, which is that the machine, a computer, data processing system, can only do computations. What we mean by computations is basically carrying out the steps of an algorithm, which are a set of rules, and following those rules, you get a specified result. We hear a lot about algorithms today, but you learn these in elementary school, like when you learn to add numbers, 2 digits, more than 1 digit, really, 2-digit numbers, 3, 4, 5-digit numbers. You don't add those numbers in your head. You add those numbers by putting one above the other, and then adding the ones column and carrying the 10, and so on and so forth. That's an algorithm. It's a set of rules by which you compute the result, and you get a result, a number, which is a result, which corresponds to whatever concept you have of what the meaning of adding those numbers together might be. So if it's, $175 in your checking account, and you get a check for $250, and you add these two things up, it's a number of dollars that are in your checking account, something like that. So it's a step-by-step logical process. And you can generalize that not just to adding numbers, but you can create, algorithms and computations for almost anything if you assign a meaning or a definition to the symbols on which you're carrying out these algorithms and these rules for. So LaRouche criticized that from two standpoints. One was the I'm sorry, my dog is making a ruckus here, but I'll ignore. So the the one was, the formal argument, similar to what Kurt Gödel made in his famous incompleteness theorems, where Gödel showed, using logical deduction, that any logical system or any system that was based on a set of rules, what is called by logicians an axiomatic system, could never be complete, and that it would always lead to conclusions which were not true or were not consistent with the system. And that's a kind of a mathematical, formal argument. And there are many other arguments that can be made of that kind of system, which shows that simply trying to reduce knowledge to rules inherently fails. So right off the bat, the idea that somehow a machine or a rules-based process could be equivalent to human thinking is just patently ridiculous. And this is a modern argument, but you can see the same argument going all the way back to Plato and Aristotle, all throughout human history. And I can give you many examples of that. I'll give you a simple one right off the bat, just to give you something, a reference point, is just think of the Pythagorean discovery that the diagonal of a square is incommensurable to the side. That is, this is discussed by Plato in the Theaetetus dialogue, but this is an idea which is known centuries even before that, all the way, even ancient Chinese mathematicians and so forth, that it's very easy to prove geometrically without any recourse to actual numbers, that geometrically the line that forms the diagonal of a square cannot be measured by the line that makes up the side of that same square. Now today might call that, and actually Greeks called it, an irrational number. But people know it today by its numerical equivalent when they think of a number that is a non-repeating decimal or something like that. But nevertheless, that's not something that can be determined or discovered by an algorithm. It can be calculated once it's discovered by the algorithm. It can be computed, the value of it, up to whatever precision you want, but it cannot be discovered. And similar example is the incommensurability between the diameter of a circle and the circle itself. So those are just a couple of examples you can keep in your head of formal examples that a rules-based algorithm doesn't work. But LaRouche also had a more profound opposition to what today we would call AI, or its employment of it, that was centered on his work on economics, because his study of economics, going back to his work in the 30s and 40s, his work on management systems and so forth, he came to the realization that economic progress depends on a characteristic of the human mind to make discoveries of physical principles that are previously unknown, or previously unknown applications of already discovered physical principles. And this then manifests itself in the form of technology and transforms man's relationship to nature and the economy and revolutionizes the economy as a whole. And that this characteristic of the creative power of discovery of the human mind to discover something that is outside the existing logical system, and that discovery would completely overthrow and transform that system, a previously set of knowledge, was the basis of all human progress and all economics. And so therefore, if one were to apply algorithmic systems to economics, it would inherently limit human progress. And therefore, it was not just a false idea that could never work. That is, put it crudely, a machine could never replicate the thinking powers of the human mind. It was monstrously evil to suggest it, especially from the standpoint that this is the way to run an economy. Now, LaRouche was not against computers or computerization. In fact, he was one of the early pioneers of application of computerized systems for process control, management systems in industrial uses, and so on and so forth. He was very much a strong advocate and active participant in the early development and application of computers to businesses. But what he was arguing against was the claims made by Wiener and von Neumann and Shannon and many of the others at the time, that this was a perfect way to organize and replicate the economy as a whole. And further, LaRouche pointed out at the time, but also more importantly, much, much later, that the inherent flaw in this belief of the, I guess, universal truth of computable systems was that this was a completely false belief, because there is no process in the physical universe real process, as opposed to a mathematical representation of a process, that is based on computability. The universe is not run by computability. It's run by much higher processes. And this, of course, was known by Kepler, Leibniz, Gauss, Riemann, Einstein, all the great scientific thinkers. But especially starting with Descartes in the 17th century and Newton, this Newtonian Cartesian system, that the mathematical descriptions of the behavior, the visible, physical, the observable behavior of physical processes was the process, is a completely false belief. To give you an example, to try and explain that abstract idea more concretely, if you think of the difference between Kepler's idea of gravitation, where Kepler actually discovered the principle of gravitation as the principle behind the motions of the planets, and he discovered that he even laid the basis for the development of the calculus and so forth. Kepler understood the idea of gravitation as what he called, he used the Latin word species, which he said was the Latin translation of the Greek word idea. It was a concept. It was a hypothesis. And he then gave mathematical construction for how that hypothesis behaved in the physical world, but that there was a distinction between the mathematical expression and the actual physical principle. Newton comes along and says, and this is the way it's accepted, gravity is a force of attraction between any two bodies in the universe, and the force of attraction is proportional, inversely proportional to the square of the distance. And that therefore the mathematical expression, the inverse square law, is the principle of gravity. And of course, the idea of it being a force between two objects, what is this force? How is it propagated? What is it in the object that attracts? All these questions are not the subject of science. So Kepler made this distinction again in a different way, that the subject of science, and this was followed by all the great scientists who made discoveries like Leibniz, Gauss, Riemann, we can go down the list, Dirichlet, the subject of science is to discover physical principles. Newton and Descartes and the tradition that followed from that is that science is merely the creation of mathematical descriptions of observable phenomena. Now, I'm being very broad brush there, so I know some people are going to email me or contact me and dispute that. But I think it's really the case. There's generally nothing to quibble about in that broad brush description. Now, of course, today it's even gotten crazier, because with the advent of the idea of artificial intelligence, or that machines can think, the proponents of that idea have inverted the proposition by now using the principles of machine computation and asserting that that's the way the human mind thinks. In other words, you start with the proposition, can a machine replicate the human mind? And then you say, well, the machine works this way, so that must be the way the human mind works. If the purpose of our design of the machine is to replicate the human mind, and the machine works this way, that must be the way the mind works. And you see this in all the characterizations of the mind that arise out of that somehow the human mind comes to its thinking process is a digital process. Now, we can discuss this more in the discussion period, but Tony will put in the chat a link to a very interesting article. I think it's 1990s article by a philosopher who wrote a lot on this subject. I think it's John Searle. It's called "Is the Brain a Digital Computer?" And he sums up these arguments. It's about a 17, 18-page paper. You don't need expertise in philosophy or anything to read it, but I would put that in there for your reference, and we can talk about that more. So that was LaRouche's prescient statements and thinking on this question of what later became known as artificial intelligence. Now, let me just point out that this was a subject of his thinking all throughout his career. In 1980, he wrote a paper that was published in EIR. Tony can put a link to this on there, called "Systems Analysis is White-Collar Genocide." Systems analysis is sort of an equivalent term or congruent term to what today is often used as AI, but it's the use of data processing techniques and systems to simulate human processes. Now, he was also in this particular article, it's quite kind of interesting to look back on it, because he was particularly critical of an organization called the International Institute for Applied Systems Analysis. I think that's the name of it. The acronym was known as IASA, which was headquartered in Luxembourg, Austria. And it was set up by a joint project between what today we would call the U.S. deep state and the Soviet elite. The two people who ran it, one was Dviram Gvishiani, who was the son-in-law of Alexei Kosygin, the prime minister at one point of the Soviet Union, and McGeorge Bundy, who was the Boston Brahmin national security advisor under John F. Kennedy, who brought us such wonderful things as the Vietnam War, and later became head of the Ford Foundation, which brought us a lot of the things that today we would describe as wokeness and controlled disintegration and everything else. So these two guys had this whole institute, which was working on establishing, very similar to what you hear today about AI, the use of advanced data processing systems to model, control, manage global processes. So LaRouche wrote a paper called Systems Analysis as White-Collar Genocide, and he lays it out. I'll just read a quick quote from it. He says, critics, let's see. In the most generous view of the term itself, systems analysis might be employed by this or that person to signify one of three things. First, it might signify a kind of systems analysis practice outside the realm of economic policymaking. Second, it might signify a form of economic systems analysis, such as the application of linear programming techniques to scheduling problems of a retail chain, an industrial corporation, or some other smaller scale application to relatively short-term projections, and he calls that microeconomics. And finally, it may signify what we have singled out for attention here, the application of economic systems analysis to whole economies or supranational complexes of economies, macroeconomics, over a period as long as a decade, a generation, or more. Critics will no doubt argue that the principles of microeconomic systems analysis are almost identical to those of macroeconomic applications to whole national or supranational economies. There is a significant degree of truth to that argument. Nonetheless, microeconomic systems analysis is often either morally neutral or sometimes useful, whereas global systems analysis is invariably evil. Now, I think that's a good characterization of what the argument around AI is, because on the one hand, you think, well, AI, and you hear people, and this is a valid argument, can do many useful things that will increase productivity and so forth. Now, I'm putting aside the hyperbolic idea that artificial intelligence is being developed in these large language models and other ideas, is going to completely revolutionize the economy such that nobody will have to work anymore and machines will do all the activity for us and so on and so forth. But put aside the hyperbolic claims, but just in terms of what its applications might be for in various firms, in production processes, in personal life, in organizing things, doing a lot of mundane tasks, basically, that take up a lot of time and help organize things. In the micro scale, it will have and could have, although to date it really hasn't shown that yet, a lot of productive uses. But then on the other hand, you have what I alluded to just a minute ago, this hyperbolic idea that it's so revolutionary that it's basically going to run our lives. And it's going to completely transform the economy so that human life is no longer going to be necessary, or it won't be necessary for human life to be productive. And we can all just, go to the beach and tap on our phones when we want to drink, and et cetera, et cetera. So that approach that somehow these kinds of systems can replace human beings, and therefore we should begin to reorganize society and to use these machine systems to guide us and to control us, or to guide human behavior, is monstrously evil. And it's evil, as LaRouche pointed out, not because an evil person might get a hold of it and use it for evil purposes. It's evil because it denies and degrades the very concept of the human mind, and you are, in a sense, destroying. It's in a sense a process to basically to take the human creativity and the human mind out of the universe, which is inherently impossible to do. Because as LaRouche emphasized, and as the empirical evidence shows, mankind survives and grows and develops by only one process. And that is what I described at the beginning: creativity, the discovery of new principles, and the physical principles, but also principles about man. And that these discoveries are then transmitted and communicated among human beings and applied socially in societies, and they transform man's relationship to nature, mankind's ability to grow and develop, whereas every other living organism, every other species of animal or plant survives in a very fixed way. But mankind has a unique process, and that's based on human creativity's ability to change man's relationship to nature and man's relationship to himself. So if you want to organize society and control human behavior based on a system that rules out that possibility, that in itself is evil. So whether it's good people or evil people controlling that system, the system will end up resulting in something evil. Now, again, that's not to say that AI and computerized systems are an evil which we should never touch. What I'm saying is that the thinking behind it has to be understood and what you're actually dealing with. If you want to put it in religious terms, I don't think it's really too far off to say that thinking of it in terms of what LaRouche was describing in systems analysis, or what some of the hyperbolic discussions around AI is very much what the Bible talks about as false idols. To say that something is going to rule the world or govern us other than the principles that is expressed, for example, in Genesis, as man being created in the image of God, which is not a physical image, but a characteristic of creativity which God bestowed on us and for which we are in his image. So that's where the evil lies. Now, let's try and flesh that out a little bit by looking at what is AI? What are we actually talking about? Because most of you have had experience with AI. You type in a question to ChatGPT or one of these engines, or even now, you open up Microsoft Word and it says, tell me what you want to say and we'll write it for you. Or you find all of a sudden that you log on to your Gmail account and Google has decided to summarize all your emails and offers to answer them for you. So it does have a kind of eerie sense of a kind of, demon in the laptop, which is some thinking entity which is able to communicate with you. And in fact, there's also a phenomenon now which psychologists and some people are concerned about called AI psychosis, where people are getting so involved in long question and answer sessions with these AI systems that they become completely obsessed with them. and lose all track of the outside world. So there's a kind of illusion that you're dealing with when you're querying ChatGPT or one of these AI systems, that you're engaging in a dialogue with some entity, not a machine. But that's all you're doing is operating a machine, and the machine is performing the operations that you have asked it to do. Now, to make this clear, it's easy to fall into that illusion because these modern machines are so complex and they move so fast and they do so many things. But even in these machines, which are so complicated, the basic principle is very, very simple. And if you look at the basic principle of these machines, and I'm going to just describe it in very simple and broad brush terms, but and it is much more complicated. And the engineers and scientists and people who design these machines and have developed them over the last 40, 50 years, really have exhibited the other principle of human creativity and human genius. But fundamentally, what these machines do is no different than what the very rudimentary machines do. In the early days of mechanical computing systems, as I said, Leibniz was one of the first to hypothesize a calculating machine. That he never built it, but it has been built since then by people following his designs. I think one of the more developed ones was a machine in the 1800s by Charles Babbage, an English mathematician and scientist. And this was a machine that was basically a system of gears and rotating dials that, if manipulated in the right way, would produce a desired result. To give something that's a little more accessible to everybody, think about one of these. I don't know how many people have had access to them, but when I was young, we used to have these big, huge calculating machines. They were electrically run, but inside the machine was a bunch of wheels and gears and so forth. And you would push down the buttons to indicate the numbers that you wanted to calculate with. And you would push another button to add or multiply or divide or subtract. And the wheels would then move, and there would be a series of wheels that had numbers drawn on them, and the wheels would turn so that the numbers in the windows would be the answer to your solution. Now, that machine has no idea what a number is, and that machine is not calculating the number, but the machine was skillfully designed in such a way that when you push the buttons, the numbers, you were positioning the gears and the wheels and then in such a way as to represent something you could interpret as a number. And when you push the add button or so forth, that activated another set of gears and wheels to make the two numbers that you put in there combined to come up with another number. The point I'm trying to make here is that the machine was not adding. It was a mechanical device which was designed in such a way that if a human being adjusted the device according to certain rules, the device produced a result which the operator could interpret as a number. And that number corresponded to the same result that you would get if you did what a human being would think of as addition. Now, it's a very useful machine because you could save a lot of time not having to do all these calculations. In fact, I'll just tell you a quick story is that one of the things about Gauss is that he was like a human calculating machine. He could do huge numbers of operations with, 10, 20 digit numbers to calculate things. But he was a genius. So most of us wouldn't be able to do it in that quick, we wouldn't be able to handle all that. So these machines are very useful for us, but they're just machine devices. Now, here's something that's, well, then as we, in the 1940s, 50s, and so forth, scientists or engineers began to think, well, you can speed up this process instead of having these gears and wheels, having to go through all the digits 1 through 10, 0 through 9. If we used a binary system, then we could, instead of having wheels, we could just have switches that are either on or off. If they're on, they're 1. If they're off, they're 0. And you can represent every number as a 1 and a 0. You can then use these switches to represent operations like and, or you can use the numbers to represent letters and combine letters and so on and so forth. And that basically introduced first, electronic switches and later transistors, and then what today we call chips, so that you could put these, create a machine that reduced all this down to ones and zeros. And you could do very quick calculations with these and manipulations with these ones and zeros, and that could simulate all kinds of important results. And there's a kind of a trick which people have become almost completely unconscious of in this notion of a computing machine, is that there's two processes. One is called software, and the other is called hardware. The hardware is the machine, and the software are the instructions you give the machine. But the instructions you're giving the machine is not really something different than the hardware. There's really if you think about it, there's really no difference than the hardware and the software. For example, in my example of the adding machine, when you push the buttons, that's your input. When you push the button that says add, that's the instruction to add. But what are you actually doing there? You're not telling it, add this. You're pushing a button, which sets in motion a whole bunch of other wheels turning, so that the wheels it sets other wheels in motion, and it turns out this representation of the sum of the numbers you're adding. Where's the software? There isn't any. And is the same thing with even the most advanced computers today. What people call software are really just ways to toggle billions of voltages on and off inside this very complex, sophisticated microprocessor, which is at the heart of the computer. Now, again, I know I'm being very simplistic and broad brush, and some of the computer scientists and software engineers and so forth out there are going to quibble with it, but I think you will agree that at fundamental principle, that's what you're dealing with. So, is that what the mind is? And here's where you see there's an evil process going on here, where neurobiologists have been trying to look at trying to use the construction, the design of these electronic machines and say that's what the brain is. So because our brain has the chemical impulses and the synapses sometimes have a voltage and sometimes don't. And so it's attributed that this is a 0 and this is a 1, and of course, very sophisticated computer programmers and software designers can take this machine and symbolically represent all kinds of logical operations. We have deluded ourselves to believe that this machine is actually doing what our mind does. And then conversely, we say because the machine does something which looks like which some people can convince themselves looks like what our mind does, then that must be the way our mind works. So that's what you're dealing with AI. Okay. So for example, and then how does that express itself in these so-called large language models? Now people think, oh, well, the large language model is doing reasoning. Either ChatGPT and all these models tend to delude you by saying, well, you can push this button and we'll give you the deep reasoning and show you the thinking process about how the model came up with with the answer to the question you asked it. But that's not what's actually going on. The way these large language models work, and they all work this way, is that everything is converted into a number, into a binary number, like, for example, words, or they divide up depending on what you're dealing with. If you're dealing with text, like the text from the internet, or you're dealing with, say, an image, everything is divided up into what they call tokens. The tokens can be a part of a word, whatever. Or in an image, it can be a collection of pixels or something like that. And then these are all converted into binary numbers. And then the large language model, and this is, again, very creative and sophisticated use of logical processes, computes probabilities for how to construct something bigger. So, for example, as a friend of mine used an example, which is a good one, if you put in the words 7 years ago, and you ask for what's the next word, the machine will calculate the probability that the next word would be our fathers brought forth on this continent, because of the use of those words or those tokens in that order in the Gettysburg Address. And then certain things are more probable and certain things are less probable. And that allows the machine to calculate the probabilities, compare the results to the inputs that it has, do a recursive type function, and try to get greater and greater probabilities and so forth. Again, I'm being very summary here, but that's what it is. And all those probability equations, although if you write them out in formal form, are very sophisticated, the computer breaks them down and approximates them using simple addition and subtraction. That's what goes on. I know people think it's a lot more sophisticated, but that's what happens. The sophistication is in the ability to design and create and engineer a microprocessor and to design the processes that are applied to that microprocessor to carry out these operations in a very quick and dramatic way. But there's no way getting around it that that's the actual physical process that is going on in the development of these large language models. So, and other AI things like, if you have a certain collection of pixels, which are numbers to the computer, and that configuration of pictures, the computer has been pre-programmed to identify that with the word dog, and then you show in a similar arrangement of pixels, the computer will say that's a dog, as opposed to a cat, which it will associate a different set of pixels with the name cat, which itself, as the computer would see it, is a number, a set of numbers, which if you ask it to produce the text, it will arrange a certain group of pixels to spell out the word cat in English on the screen. So that can be very useful. It can produce interesting results. It can help you do research and search the web a little bit more efficiently than a Google search or something like that. I've used it. But is that thinking? And the answer is clearly no. That's not the way the human mind thinks. So that right there is a inherent, I think, indicates an inherent limitation to what we're going to get out of these AI large language models. Now, you're already beginning to see people indicate that, because you have the, like, for example, the latest version of ChatGPT 5 came out and has generally been panned. Well, it's not that much different than 4. You have the fact that, as I said in the beginning, large numbers of companies are trying to utilize these large language models, and it hasn't really increased productivity that much. Some companies are using it for customer service reps, so that when people call in, the customer service rep can use a large language model that's been trained on the service manuals of whatever that company deals with, and can use that large language model to try and help solve the questions that are coming in customer service. And that might be a slight increase in productivity for that particular firm. Whether or not it's an increase in productivity for the economy as a whole is a whole nother question. Nevertheless, promise of that has created a huge financial incentive to invest in the companies that are involved in these projects, both the companies that are making the large language models themselves, as well as the companies that are making the infrastructure, the chips, the power systems, et cetera, on which these large language models the machines themselves. So what's the effect on the economy as a whole? It's very hard to say right now. We'll know as things develop. There's some interesting possibilities for improving productivity in industry itself, especially related to robotics, that may really increase productivity. So far, there are applications, like in China, they have a lot of these, what do they call them? Lights out factories, where all run by robotics. They don't need lights. Everybody knows about Amazon warehouses, robotic picking system in their warehouses and these kinds of things. So it has a lot of applications in those areas. But what its overall effect on the productivity of the economy is, I think, still up in the air. And there's nothing on the horizon that justifies the huge amount of investment which is going in right now. But that doesn't mean that there's anything wrong with a huge amount of investment going into speculative things. But if it doesn't lead to actual products and increases in productivity, you're going to ultimately have a shaking out of that, as we saw, for example, with the dot-com bubble. One difference, I think, between what the infrastructure around AI and the infrastructure that was built up around the dot-com bubble is that there was a lot of infrastructure built that was not being utilized by a lot of these internet companies in the late 1990s, early 2000s. Whereas today, the infrastructure we have is way behind what is being demanded by a lot of these computing systems. And you see that by the requirements for electricity and the panic, or I shouldn't say panic, but the emergency desire to massively expand our electrical production in the United States and everywhere else in the world. The beneficial byproduct of that is it seems to have sparked a renewed push for nuclear energy, both the large nuclear power plants, and the Trump administration is working on that, as well as, all the way down to micro and miniaturized small nuclear reactors. The micro reactors are very small 1 megawatt reactors, which might just be used to run a particular factory. So if we get out of that, a lot of investment in electrical production, that in itself increase productivity in the economy, especially if we get a surplus of electricity, we'll begin to bring around electrical prices, and we increase the power grid or even decentralize it so that you have more electricity available. That, for example, would have, I think, a positive effect on economic productivity in the United States. So that's what I think current state is. I've thrown a lot of things out, and I don't want to keep talking. And there's a lot more I could say, and maybe in the Q&A, or Tony might have something to add, especially about the more fundamental questions that LaRouche raised and that I discussed at the beginning. And we can get into more detail of that in the Q&A. But I think I'll stop there for now. And maybe I either demystified the current debate around AI, or maybe I made it more mystical for you. I don't know. So we'll find out in Q&A.
Yeah, I think it's extremely useful. I mean, for LaRouche, as you implied, from the beginning, and he was in it from the beginning, from the 40s, from the time that Wiener's book first came out, which I think was around 45. He saw it as not merely a practical question, but a deep philosophical and moral question. And it is that today, as you indicated. I'm sure people will have a lot to say about it.